Hello friends, today's question. A thin rod of length L and uniform cross-section is pivoted at its lowest point P inside a stationary, homogeneous and non-viscous liquid. The rod is free to rotate in a vertical plane about a horizontal axis passing through P. The density D1 of the material of the rod is smaller than the density D2 of the liquid. The rod is displaced by a small angle theta from its equilibrium position and then released. Show that the motion of the rod is simple harmonic and determine its angular frequency in terms of the given parameters. So we are given this vertical rod. That's the rod which is in the vertical position, and the density of the rod is D2, density of the liquid is, density of this rod is D1, and density of this liquid is D2, and it is given that density of liquid is greater than density of the rod. Okay, this is important. If we can discuss that later on, how this plays a very important part. And this is point P, about which it pivots and making a small angle theta with a vertical, and we have to prove that as soon as it is disturbed from the equilibrium position, it executes a SHM, and then we are going to find out its angular frequency. So we can divide this into two cases. First case, when the rod is vertical. So here this is a rod and density of the rod is D1, and this is a pivot point P, and it says that it is free to rotate along the axis which is vertical. It is free to rotate and pass it through point P. And let us suppose this is its center of mass. So about the center of mass, there will be weight acting downward direction. Let us suppose that is W. And in the upward direction, there will be a buoyant force. Let us call that FP. Okay, and liquid is always present there. So this is initial condition, and there is a final condition in which the rod is pivoted about this point P and making a small angle. So this is the final position of the rod after pivoting about point P, making the angle of theta with a vertical. Now here also there will be a weight acting in the downward direction, and we are going to have a buoyant force FB which will be in the upward direction. So this is our initial condition, and this is our final condition. And bear in mind that it is given the density of this liquid is greater than the density of the rod. Okay, so because of this, we can say that the buoyant force that will be acting on the rod will be on the higher side as compared to the weight. So let us consider first of all the initial condition. The forces acting on the rod first force will be the weight of the rod, which we said let it be W, and it will be acting in the downward direction. Weight of the rod acting downward, at center of mass. Okay. So total length is given as L. So it will be L by 2 and L by 2. Okay, this point is our center of mass. So acting downward at center of mass located at L by 2 from point P. So therefore we can say that this W will be equal to our mg, and mg can be written as A multiplied by length, and we have this d1 and this is our g, where m is the mass of the rod and d1 is given as density of rod and L is the length of the rod. Length of rod, and A is area of cross section of rod. Next we are going to find out the buoyant force. Let us call that FB, and this acts upward at the center of mass acts upward at the center of mass, as the rod is, you can say, homogeneous, and the liquid is also homogeneous. So therefore from here we can say this FB will be equal to V multiplied by T2 multiplied by G, where this V is volume of the rod and T2 is our density of the liquid. So we can write this as FB, V will be equal to A multiplied by L and D2 and G, where A is the area of cross section of rod and L is the length of rod. So we found out that what will be our buoyant force and what will be our, you can say, the weight of the rod, both W as well as FB. Sorry. Next, we say for the final condition when the rod is displaced with the angle of theta. So as it is displaced by the angle of theta, there will be a storing torque that will be acting on this rod, which will try to bring it into the equilibrium position, and the equilibrium position is said to be vertical position. So we have restoring torque upon displacement. By angle theta. Therefore we can say when rod is displaced by a small angle, theta, with the vertical so under this condition also both weight, that is W, and our buoyant force continue to act through center of mass. Continues to act through center of mass. But since the rod is tilted, you can say their forces acts along the line through the point V, which results in the torque. So because now the rod is tilted, so we can say the forces no longer act along the line. Okay, previously they were acting along this line P. Now they are no longer acting along the line P, along the vertical axis. So as they are no longer acting along this line, there will be a you can say torque will be the resulting force because of the shifting of the rod with respect to the vertical. So both W and FP continues to act through the center of mass, but as the rod is tilted, these forces between W and FP no longer acts along the line through pivot point P, along the line through pivot point P, and this results in torque, which results in torque. Because previous position of the equilibrium was only because both the weight as well as the buoyant force were acting along the pivot axis. So there was no torque because of these two forces. Now it is acting at a different point, which is not along the axis of the pivot. The axis has been shifted. So therefore we can say the horizontal component of the force difference. So next we find out the horizontal component of the force difference. Horizontal component of force difference. So although the rod is moving in the vertical plane, but still there is some horizontal distance that through which the rod has been moved. So you can say the horizontal displacement due to tilt of the rod introduces a net horizontal force difference. A net horizontal force difference, and as it is given that density of the liquid is greater than density of the rod, it is given to us. So from here we can say the buoyant force will be greater than the weight. Okay, and this results in an effective horizontal restoring force. Thus there is effective horizontal restoring force component proportional to theta. And let us find out what will be this restoring torque. Restoring torque. Now this horizontal component is going to generate a restoring torque. This horizontal component generates a restoring torque around the pivot point P. Around the pivot point P, which tries to bring the rod back to its equilibrium position. And this equilibrium position nothing but the vertical position. Okay. Therefore, we can write the restoring torque tau about the point P. So you can write restoring torque tau about point P will equal to minus net force multiplied by the perpendicular distance. Okay, that's a standard formula for the torque. And our net force, you can say that tau P net force will be the buoyant force minus the weight, and we have the perpendicular distance, and perpendicular distance will be L by 2 sine of theta. Okay. You can just draw a approximate of that also. So this is our vertical, this is point P, and the rod is now in this position. So this is the center of mass, and it is along the vertical, it is having angle of theta. So this distance is our L by 2, so this angle will be equal to theta, so the perpendicular distance will be equal to L by 2 sine of theta. So in the question itself it is given that this theta is small, so you can say for theta is small, sine of theta can be approximately equal to theta. And from this we can write that our tau about point P, torque about point P is equal to minus Fp omega, and this we can write as L by 2 multiplied by theta. Now we substitute the value of, so we can approximate it. Fp and W in this equation we get that minus, and we have AL D2G minus AL D1G multiplied by L by 2, and this is our theta. So we can simply take something as common. So we get this is tau about point P. We can take AL G as common, so this becomes minus AL G, and this is 2, and this is L, so this becomes AL square G, and we have d2 minus d1 multiplied by theta. Let us call this as equation number 1. And there is a slight, you can say, because of the tilt of the rod with respect to vertical, it will be having some angular acceleration also. Let us call that angular acceleration as alpha. So you can say equation of motion in as a rotational motion rather. Equation of rotational motion. We can say for rotational motion, torque, and it is rotating about point P, so this will once again torque about point P will be equal to I multiplied by alpha, where I is the moment of inertia about point P. I is moment of inertia about point P, and alpha is the angular acceleration. Angular acceleration, and this can be given as double derivative of theta with respect to time t. And I is the moment of inertia about point P, and this point P is at the end of the rod. So from here we can write that our I will be equal to 1 by 3 ml square, and we substitute value of mass m. So we get that I will be equal to 1 by 3, and m is our AL d1, and we multiply by L square, and alpha is our double derivative of theta with respect to time. So we substitute in this equation, we get tau at point torque at point P, we have 1 by 3, and this is our AL d1 L square multiplied by double derivative of theta with respect to time. And let us call this as equation number 2. So both are the torque at respective points P, so therefore we can equate them. So we can say from equation 1 and 2, from equation 1 and 2, we substitute, we can say we equate them, and we get this as minus 1 by 2 EL square d2 minus d1, this is g multiplied by theta, is equal to 1 by 3, and we have AL d1 L square and multiply by double derivative of theta, and this AL a square and square goes away, so we are left with 1 minus 1 by 2, and this is d2 minus d1 g of theta is equal to, we have here 1 by 3L d1, and this is double derivative of theta with respect to time. So just adjust some things, making left to right, we can write this equation as double derivative of theta square, and this becomes plus, this will be our 3 by 2, and we have here g by L, g by L, and this becomes d2 minus d1 divided by d1, and this comes theta is equal to 0. And this is nothing but standard equation for SHM. We can make a comparison. We can say this is the equation of SHM, and we can also make a comparison with the standard equation, that is our plus omega square theta is equal to 0. So therefore from here we can say our omega square is equal to, we have 3 by 2 GL, and this is T2 minus T1 upon D1, and we get that is angular frequency omega is equal to square root, this is 3G upon 2L D2 minus T1 upon D1. So this is our final answer, which was supposed to find out angular frequency in the given parameters and prove that it's a motion of simple harmonic. So this proves that motion is SHM, motion of the rod, is SHM, and this is the frequency, or we can say angular frequency rather. Let me write it here. Angular frequency of the rod. Okay. So this completes the question. Thank you.